Good morning. During this presentation, I will present our work based on the chlorine isotopes of chlorides in pore fluids of clay-rich sediment of the oceanic crust. We studied the fluids of 18 sedimentary piles from the main oceans of our planet. They were deposited in diverse geological contexts, basins, diversion zones, conversion zones, and elsewhere. These sediments cover a wide range of sedimentation rates, from fast to very slow, and a wide range of compaction rates, that is, reduction of porosity as a function of depth. So, with this set, we have a good sampling of the diversity of clay-rich sediments at the bottom of the oceans. In terms of chloride concentration, the pore fluids analyzed remain very close to the concentration of seawater. In only two cases, there is a decrease in chlorides, pile 1150, Aquatian Prism east of Japan, and pile 997, continental margin west of the Atlantic Ocean, where gas hydrates were discovered. In only one case, there is an increase in chlorinity, pile 1201 from the Philippine Basin. Generally, in the literature, these variations are interpreted as produced by water intake or consumption. Chlorides are considered as inert. On this slide, the depth profile of the delta 37 chloride are presented. It is immediately noticeable that all the values start from 0, which is the delta value of seawater at the seafloor, and gradually decrease with depth. Out of 270 delta measured, only 3 values are above that of seawater. Very negative delta value below -3 are observed at depth, whatever the geological context, in sedimentary rift basins, on continental margins, in subduction zones, and elsewhere. Since the fluids initially had the composition of seawater, one must wonder where the missing 37 chlorine went. For the other main components of these pore fluids, there is a very classical systematics described since the first IODP drillings. That is, to say according to depth, an increase in calcium, a decrease in magnesium, a decrease in O18. These changes are explained by the alteration of the original minerals in the sediments, in particular the growth of clays, which pumps magnesium and O18 from the fluid and releases calcium into the fluid. However, in many cases, this process is not intense enough to explain the magnitude of the decrease in O18 and the increase in calcium. As a consequence, the flow of calcium and O18 depleted water from below, that is, from the underlying basalts, is invoked. This figure is surprising. It shows that in the fluids of these sediments, the delta weighting of water is correlated with the delta 37 chloride of chlorides. This correlation is observed everywhere, except for a few particular depths where external fluids were injected in the piles. Only site 997 does not show any correlation. Whatever the geological context, the pore fluids are on the main train. The two extremes of the main trains are seawater and pole A1', previously defined. Only the pore fluids of 1201 are clearly shifted above the main train. On this figure, we can examine the individual correlations. They are very strong and very significant. The R squares are all above 0.75 and many are above 0.9. In this figure, we compare the ellipses at 86% probability of the slope and the intercept of these lines. This reinforces the idea that the majority of the lines are very close. They are in the small membrane box. The other lines are clearly different: 1026, 645, 1150, and obviously 1201. We note that the slopes of these lines are close to 1. This indicates that the variation in delta O18 are of amplitudes comparable to those of delta 37 chlorine. We will now try to understand what can make the delta 37 chlorine vary. At low temperature in oceanic sediments, the geochemistry of chlorides is very simple. Chlorides remain in the form of chlorides because they are not involved in oxidoreduction reactions. Chlorides do not enter significantly into minerals or organic compounds. Chlorides are not or only slightly absorbed on mineral surfaces. Chlorides, therefore, are essentially in the fluid phase of the sediment. The chlorides would be, therefore, traces of processes specific to fluids. Here is a list of 4 processes known to change the delta 37 chlorine in fluids. Among these processes, diffusion and gravity can be eliminated. They produce 2 small fractionations or 37 chlorine enrichments in the sedimentary piles. Advection of external fluid into sediment by mixing, the delta 37 chlorine will change if the advected fluid has a different delta 37 chlorine than seawater. Ionic filtration, when a fluid is transported in membranes, the passage of chlorides is controlled by the mobility of the chlorides. Advection. It is quite simple. The fluid pore A1', depleted in O18 and 37 chloride, is injected from below into the sedimentary piles, whatever the geological context. This results in straight lines in the delta O18, delta 37 diagram because the chloride concentrations do not vary much. However, the process that generates the 37 chlorine depletion of A1' remains unknown. It cannot be a sequestration of 37 chlorine in the alteration minerals, as this would imply delta 37 chlorine higher than 200 per ml to explain the depletion of 37 chlorine in the fluid. This is because low temperature minerals have very low chloride concentrations compared to pore fluids. Ion filtration. The idea of Phillips and Bentley only exists in theory. For the moment, no experience has shown it to exist. When a fluid is transported through a negatively charged membrane, such as clay, the chlorides are repelled by electrical force. 35 lighter and therefore mobile would be repelled further than 37, heavier, therefore less mobile. As a result, the 37 chloride would have a better chance of passing through the membrane. Globally, the chlorides would be enriched upstream of the membrane. Ionic filtration must occur in the sediment, since the porosity decreases as the depth increases. This is the compaction effect. By necessity, in order to conserve the masses of fluid and solid in the sediment, the fluid goes down less quickly than the solid in the sedimentary column, and the filtration takes place. The problem is how to quantify ion filtration effect during sediment compaction. Is it large or not? We can do that simply from the evolution of porosity versus depth and by writing conservation of the solid part of the sediment. At a given depth z, the proportion of initial fluid lost by the sediment is given by F fluid. The proportion of initial chlorides lost by the sediment is given by F chlorides. For the sedimentary piles of this study, we have F fluids between 0 and 0.7 and F chlorides between 0 and 0.7. Generally, the two Fs are equal because the concentrations of chlorides do not change very much. Does filtration require significant isotope fractionation to explain the delta 37 chlorine data? To estimate it, we built a model of chloride evolution during the compaction of the sediment. It is based on four equations: reduction of the porosity, conservation of the mass of fluid and the mass of solid, and conservation of 37 chlorine and 35 chlorine. This model makes it possible to estimate the value of the isotope fractionation during filtration, necessary to explain the decrease of the delta 37 chlorine, and the value of the partition coefficient of chloride necessary to explain the evolution of chlorinity. In this box model, two possibilities are considered. Either the excess fluid remains confined in the pile, CSP model, or the excess fluid escapes at all the times through cracks and faults, OSP model. Eventually, the top of the pile is open to the ocean, CSP and OSP models, or not, CSP WBL model. Here are outputs from the filtration model, which gives the evolution of the delta 37 as a function of the amount of chloride lost, F chloride, which is a function of depth. The OSP and CSP variants are also displayed. We see that the greater the isotopic fractionation of chlorine during filtration, the greater the depletion in 37 chlorine in the fluid. For fractionation of 1.005, the model generates delta 37 chlorine as low as -9, the extreme value measured in our fluids. Here are the filtration model parameter adjustments for 5 delta 37 chlorine and chlorinity profiles. In summary, we see that the values of the partition of chloride, KCl, obtained are close to 1. This means that filtration would have little effect on chlorinity. This is in contrast to the predictions of Phillips and Bentley. The chlorine isotope fractionations obtained are systematically above 1, in the 1.00 to 1.006 interval. This is in agreement with the predictions of Phillips and Bentley. Filtration model adjustments can also be made for the decrease of the delta weighting of pore fluids. When the values of the fractionations necessary to explain the oxygen isotopes are plotted against those of chlorine, a coarse line is obtained. There seems to be a correlation with the mineralogy. Large fractionations are obtained when the sediments are rich in smectite, medium fractionation for halite chloride-dominated sediments, small fractionation for kaolinite-dominated sediments, and no fractionation for carbonate-dominated sediments. We now come to the conclusions. The most important conclusions are the 18 depletion and 37 depletion in pore fluids are strongly correlated. This depletion can be explained by ion filtration in clay membrane induced by compaction, and these depletions are correlated with the mineralogy of the clays in the sediments. Thank you.